The hypothetical reaction A plus B yields C plus D is shown in this potential energy diagram. From this diagram, we can determine the activation energy, which is the amount of energy needed to activate or start the reaction. For the forward reaction, where A plus B yields C plus D, the activation energy is the amount of energy from the reactant level up to the hilltop. And that is going to be a positive 60 kilojoules. We're going to skip the reverse reaction and come back to it. In order for this reaction to go forward, it needs 60 kilojoules of energy put in. The delta H, or the heat of this reaction, is always the difference between the reactant level and the product level, with no matter and no mention of the activated complex or the activation energy. It is always the starting level and the ending level and that difference. In this case, the heat of reaction is negative 30 kilojoules. So it is a negative delta H for this case, which means the reaction is exothermic. The EA will be a positive number in both situations, the activation energy of the forward reaction, which I'm labeling in blue. The activated complex is the part of the reaction that has the highest energy, and it can also be thought of as the transition state, where bonds are being broken and made, and it's the highest potential energy for the whole reaction. It is also the least stable, and therefore short-lived. The activated complex is the value at the highest energy level, which is 100 kilojoules. If you were to run this reaction in reverse, say starting at CD and trying to create A and B, you would have to go from the level of CD to the hilltop. So the EA of the reverse reaction is 90 kilojoules, which means that it takes more energy to reverse this reaction than to run it forward as far as the energy of activation. If you were ever asked to determine the activation energy and it doesn't mention if it's forward or reverse, you always assume that it's forward because that's much more common to talk about. So the forward activation energy is always the difference between the reactant level and the activated complex level, so 40 and 100. The activated complex is the value of the highest position, and the heat of the reaction is always the difference between where it starts and where it ends, and that absolutely needs a sign because a negative change means that the reaction is exothermic. Take a look at this example, pause the video, and see if you can determine the activation energy in the forward reaction, the heat of the reaction, and also the energy of the transition state or the activated complex. The activation energy goes from 20 at the reactant level up to the hilltop, and the difference between 20 and 70 is 50. So the activation energy is 50 kilojoules in the forward reaction. The heat of the reaction is always the difference between the reactant level and the product level, and that alone. So the heat of the reaction is equal to the difference between 20 and 40, and in this case it's positive 20 kilojoules. The energy of the activated complex is 70 kilojoules. Can you determine the heat of the reaction for the reverse reaction? The heat of the reaction for the reverse reaction would simply be negative 20. However, the activation energy for the reverse reaction would not just be negative 50. You have to actually look at the reaction energy diagram and see that it goes from 40 to 70 in the reverse reaction, meaning the reverse reaction's activation energy is 30 kilojoules. But what is truly happening at this transition state, at the high energy activated complex. At the activated complex, bonds are being broken and bonds are forming from reactants to products. So in this example, we have a green atom that is breaking the bond with the blue atom. And at this time, the blue atom is forming a bond with the pink atom in the most simplistic representation of this. So this is the bond being broken, and this is the bond being created. How does a catalyst change this reaction? A catalyst speeds up both the reverse reaction and the forward reaction by lowering the activation energy via some pathway. It does not change the heat of the reaction. It does not change the potential energy of the products, nor does it change the potential energy of the reactants. However, through some pathway, it can lower the activation energy and make the reaction faster. Effectively, it lowers the hilltop, or lowers the energy of the activated complex. Here is how a catalyst would be represented on a reaction energy diagram. A catalyzed pathway will still have the same reactant energy, but it will have a lower activated complex. So the only change for the catalyst is that it lowered the activation energy. Through some lower energy pathway, the catalyzed reaction has lowered the activation energy in this example from 50 down to 40. As a result, it would also change the energy of the activated complex, or the energy of the transition state, making it just 60 for the catalyzed forward reaction. Notice how the activation energy for both the forward reaction and the reverse reaction decreased. As a reminder, catalysts speed up both forward and reverse reactions by lowering the activation energy in both directions. It does not change the heat of the reaction. It still ends here, and it still starts here. Therefore, it is still a positive 20 kilojoules. On this diagram, a catalyst may lower the activation energy significantly. In this case, the activation energy is now just 20 instead of 60 in the forward reaction. That was an overview of reaction energy diagrams and both catalyzed and uncatalyzed pathways, and determining activation energy, also the heat of reaction, and the activated complex or the transition state.